Howdy, welcome to Elementary Statistics. I'm Lance Curtis. This is the lecture for section 9.2, two means, independent samples. Here in this lecture, we're going to look at evaluating the claim for two population means when we have independent samples. So naturally, the first thing we're going to do is talk about what are independent samples, and then we'll get into the requirements for our methodology, followed by how to form and test the hypotheses, how to construct confidence intervals on the difference between two means, and then we'll get into using StatCrunch to perform these same functions. So let's dive in. So here we have methods we're going to present for using sample data from two independent samples to test hypotheses made about two population means, or to construct confidence interval estimates of the difference between two population means. Now, in this instance, we're going to have three possible situations. The first situation we could confront is that we have two population standard deviations that are unknown, and we assume they're not the same. Second, we could have the same two population standard deviations that we don't know what they are, but this time we're actually going to assume that they are the same. And third, we could actually know what the two population standard deviations are. They could be equal to each other or not. It doesn't really matter because we know what they are, so we don't need to make an assumption about whether they're equal to each other or not. In the real world, we see that situations 2 and 3 are typically not seen. They do appear from time to time, but they are very infrequent. And that infrequency will lead us to confine our attention to looking at confronting situation number 1. So we're going to have two population standard deviations. We don't know what they are, and therefore we're going to use a t-score and not a z-score for our test statistic. And we're not going to make any assumption about equality. We're also going to assume that we're going to have independent samples. So samples are dependent, as we learned previously, when we have values from one population that are related or that have a relationship that allows them to be paired with unique data points from another set, another population. If we don't have that connection, then we have independent samples. Common examples of dependent sample data are where you take two measurements from the same subject. So you have before and after data. Or you have data on matching pairs, so husband and wives, or twins. These are examples of dependent sample data. The methodology that we're going to look at in this particular lecture requires independent samples. So if we have dependent samples, we do have a methodology for treating that, and we'll get to that in the next lecture because that's what the next section is all about. But for purposes of this lecture, in this section, 9.2, we're actually looking at samples that are independent. So, for example, if we have data collected for males and females to compare between genders, that would be classified as independent data because no one man can be paired with any one woman. However, if we have data collected from husbands and wives, now that's a different story because that marriage relationship provides a connection between one unique data point in the first group with another unique data point in the second group. And so that data would be characterized as dependent. So assuming that we have independent samples, there are some requirements that we need to have met before we can use our methodology. The first, as we said before, we're not going to know the value of either of our population standard deviations. And we're going to tweak the situation a little bit. We're not going to make any assumption about their equality. Second, as we just got done explaining, we want to have independent samples. Third, both of our samples will be simple random samples. Fourth, each sample either has a sample size greater than 30, so that we have central limit theorem that comes in and says we can use the normal distribution as an approximation, or our data set already is normally distributed. You're also going to see that we'll use much of the same notation that we've used previously. So mu is still the population mean, sigma is still the population standard deviation, n is the sample size, x bar is the sample mean, and s is the sample standard deviation. But now that we have two populations to look at, we also have two samples, and so we're going to use a subscript 1 to represent population 1 or sample 1, and that will distinguish it from the parameters and statistics for which we use a subscript 2. The subscript 2 will represent population 2 or sample 2. We're going to look at forming the hypotheses for our hypothesis test. As always, the null hypothesis, H0, is by definition a statement of equality. So we can write that the population mean for the first population is equal to the population mean for the second population, mu1 equals mu2. But if we subtract mu2 from each side of this equation, we're left with the algebraic equivalent mu1 minus mu2 equals 0. So sometimes you'll see the null hypothesis expressed one way, sometimes you'll see it the other, but it doesn't matter, they're saying the same thing. The alternative hypothesis will still typically reflect the claim, assuming there's no semblance of equality expressed in the claim. Then we can actually write, for example, mu1 is greater than mu2, or mu1 is less than mu2, or mu1 is not equal to mu2, just as we've done previously. Sometimes, however, you'll see the algebraic equivalent, mu1 minus mu2, is greater than 0, or less than 0, or not equal to 0. When we form hypotheses for two samples, we're going to use the same conventions we used when forming the hypothesis for one sample. Then we're going to calculate a test statistic. Only this time, we don't know what the population standard deviation is, so therefore we're going to be using a t-score, and we're going to use this monstrosity of an equation to calculate it. It's actually not that bad, but looking at it, it's not exactly, 2 plus 2. You got to put a little bit of work into it. Typically, we're going to assume that the difference between the population means is 0. Why do we do this? Well, we don't know what the population standard deviations are. We're not making any assumption about their equality. However, the methodology that we're using is very similar to what we've used before, and that methodology assumes that the null hypothesis is true. Well, the null hypothesis is mu1 minus mu2 equals 0. So for that reason, we're going to substitute 0 in for mu1 minus mu2. The other variables in our equation come directly from the problem statement. So we'll plug those in, calculate out a test statistic, and then we have what we need to evaluate our claim. We'll then use the test statistic to calculate a p-value using a t-table or software, or we can take the test statistic and compare it directly with a critical value. Critical values for two samples work the same way as they do for one sample. And the criteria that we're going to use to evaluate our hypothesis test is very much the same. So if we're inside the critical region, reject H0. If we're outside the critical region, then we're going to fail to reject H0. Now, because we're using the t-score, there's going to be a degree of freedom involved. So how do we calculate that? What sample size do we use? I mean, it's easy to answer that question if the sample sizes are the same, but the sample sizes don't have to be the same. So what do? Well, the typical convention that's used in this situation is to use the sample size that is the lower of the two. So take whichever sample size is less, and then take one away from that, and that is the degrees of freedom that you're going to use to calculate your critical value. Confidence intervals for the difference between two population means work much the same as they do with the one population mean. So first we find our margin of error E, and that is found by this equation that you see here on the screen. Once we have our margin of error, we can then go to our general form to construct our confidence interval. Again, notice we're not looking at just one parameter or one statistic. We're looking at the difference between two populations, the difference between two sample statistics. But everything else works just as we've seen it work previously. Let's look at an example to illustrate how this is applied. So we have researchers who conducted trials to investigate the effects of color on creativity. So subjects were asked to think of creative uses for a brick. Some subjects were tested in a room with a red background. Other subjects were tested in a room with a blue background, and responses were given by a panel of judges. So by testing them in the different colored rooms, we can see if the color has any effect on creativity. We are asked now to test at the 1% significance level the claim that blue enhances performance on a creative task. So that means that the mean number of responses for people in the blue room is going to be higher than that for the people that were in the red room. First, to evaluate the hypothesis test, let's collect some summary statistics. Again, I like to use the table form because it keeps everything in line. It helps me know that we've got all our I's dotted and T's crossed. So here you can see that we have sample sizes and then sample means and sample standard deviations. I just collected those from the from the problem statement. For my degrees of freedom, I'm going to take the sample size of 35 and subtract 1. And I'm taking the 35 because that's the lower of the two. I have 35 and 36. So I take the lower of the two, subtract 1, and that's my degrees of freedom. So here I'm going to have 34 degrees of freedom. Now, let's check our requirements to make sure those are met. First, values of the two population standard deviations are unknown. We don't know what they are, and we're assuming that they're not equal. Second, the subject groups are independent. There's no connection between any unique person in the blue room with any unique person in the red room. Samples are simple random samples. And both sample sizes are greater than 30. So we don't need to use central limit theorem. Actually, central limit theorem says that sample size is greater than 30. We can just use the normal distribution to approximate. So we don't need to check for normality in our samples. Now we can form our hypotheses. First, as always, we want to represent the claim symbolically. So the claim here is that blue enhances performance on creative tasks. That means that people in the blue room should produce, on average, more creative ideas than people in the red room. We're going to assume that the people in the red room are from group 1 and people in the blue room are from group 2. The reason why we're doing this is because the people in the red room were mentioned first, people in the blue room are mentioned second. So we're going to go with that assumption that subscript 1 goes with the red room, subscript 2 goes with the blue room. Because we're saying that blue enhances performance on creative tasks, that's going to translate into mu1 is less than mu2. Now we're ready to write our hypotheses. The null hypothesis, as always, is a statement of equality. So mu1 is going to equal mu2. The alternative hypothesis typically reflects the claim. Here we have a claim with no semblance of equality in it. So therefore, we just mirror that and adopt it for our alternative hypothesis. mu1 is less than mu2. Note that we have a match between our claim and our alternative hypothesis. Note also that we have a one-tailed test. The less than inequality sign in our alternative hypothesis tells us that we have a left-tailed test, which is a one-tailed test. Now we're ready to test our claim. So we can calculate our test statistic and compare it with our critical value. The test statistic is calculated with this monstrosity here. So we plug in what we know, punch this out on our calculator, and out comes negative 2.979. We can get the critical value by using either a t-table or the t-calculator inside StatCrunch. So here we have put in our significance level alpha, which is 1%, and that area is going to be bounded by the critical value, which in this case is negative 2.44. So now we compare our test statistic with our critical value, and we see that negative 2.979 puts us over here inside the rejection region. Therefore, we reject H0. Alternatively, we could have used the p-value compared with our significance level. The p-value will come out if we put in the test statistic that we calculated. That test statistic is the boundary for the area that is the p-level, the p-value. So when we do that, we get a p-value of 0.0027. That number is less than 0.01, which is our alpha. So therefore, we are inside the rejection region because we can fit the area for the p-value inside the area for alpha. We're inside the rejection region, and therefore we reject H0. Now, because we rejected H0, we're going to accept the claim that blue enhances performance on creative tasks. But the way we word our conclusion is more like this. There is sufficient evidence to support the claim that blue enhances performance on creative tasks. Remember that this first part, there is sufficient evidence, comes from the fact that we rejected H0. Had we failed to reject H0, we would have instead said there is not sufficient evidence. The next part, to support, comes from the fact that we have a match between our alternative hypothesis and our claim. If there was a mismatch between the two, then we would have said warrant rejection instead of support. We can also construct a confidence interval to test our claim. Now, just as we saw earlier with confidence intervals for resolving hypothesis tests on the mean, those confidence intervals were found to be just as reliable as the more formal methods of hypothesis testing. So we can use the confidence interval to resolve a hypothesis test claim on a mean value. Let's test that in this case. First, we calculate our margin of error, and then we can use that to create our confidence interval. So our margin of error is calculated using this equation. We plug in what we know, punch it out on our calculator, and out comes 0.475. This is our margin of error. Now we go to our general form, we substitute in what we know. So we have our two sample means and our margin of error. We put those into the equation for the general form, and out comes a lower limit of negative 1.055 and an upper limit of negative 0.105. So now the key question is 0 inside the confidence interval? Here 0 is not inside the confidence interval. And therefore, we're going to conclude that there is a difference in the mean number of creative ideas each group produces. Furthermore, because the blue room is represented by mu2 and the red room is represented by mu1, the value for mu2 has to be greater than mu1 in order for this number to come out negative. And that's what we see. All the numbers inside the confidence interval we just calculated are negative. So that means mu2 is greater than mu1, which means blue is shown here to enhance creativity more than red. Let's look at how to actually conduct hypothesis testing using StatCrunch. So again, a single simple option is going to provide most of what we need. So we're going to go stat, tstat, toSample with summary. Enter in our information. Again, the same convention that we saw with proportions is going to hold here. If you're not told which sample to use with the subscript 1, then the one that's mentioned first goes with sample 1. The one that's mentioned second goes with sample 2. Make sure you have a match here with your inequality drop-down with your alternative hypothesis. And once you have all that information in, go ahead and press compute. Oh, and one more thing that we need to mention is that when you're testing for two means, there's this added extra where you can pool the variances. And it used to be that the default option was to have that box checked. So when you're working these problems, you'd have to go through and uncheck that box every time. Well, I guess news of this got back to Pearson and they decided they were going to upgrade software. So they did that. And now the default selection is that the variances are not pooled together. And this is what you want for the problems you're going to be working. So it's always a good idea to make sure to check that that box is unchecked. It will come up naturally unchecked, but just make sure that it's not checked when you're working your problems. Once you have all your information in, press compute. Out comes your results window, and you can read the test statistic and the p-value right off the results window. As always, your test statistic is the next to last number listed in the results window. The p-value is the last number to be listed in the results window. Let's look at an example problem to illustrate how this is done in StatCrunch. So here we have a table listing results from a study of the number of words spoken per day by randomly selected men and women. Now we're asked to answer the following questions with respect to the claim that men speak fewer words per day on average than women. 1. What is our hypothesis? What are our hypotheses? 2. What is the test statistic? 3. What is the p-value? 4. Use a 1% significance level to decide whether to reject the null hypothesis. And 5. What do you conclude from the hypothesis test? Notice that we're giving the group of men the subscript 1 and the group of women subscript 2. This is because men were mentioned first in the problem statement. Women were mentioned second. So that's why the subscript 1 is going with the men and the subscript 2 is going with the women. Let's look at these questions one at a time. So the first one is, what are our hypotheses? As always, we're going to start with the claim that's being made. So here the claim is that the average number of words by men is less than that spoken by women. So the average for men, mu1, is going to be less than the average for women, which is mu2. We can also express this as mu1 minus mu2 is less than 0. Now, remember that the null hypothesis is by definition a statement of equality. So mu1 minus mu2 is going to equal 0. Next, the alternative hypothesis typically will directly reflect your claim. Here our claim has no semblance of equality to it, so we just adopt it for our alternative hypothesis. Note the match between our alternative hypothesis and our claim. Notice also that because the alternative hypothesis uses the less than inequality sign, it's just like an arrow pointing to the left, and we have a left-tailed test. This is a one-tailed test. So now the next question that we're asked is, what is a test statistic? So in StatCrunch, go to Stat, T-Stats, one sample with summary. And you're going to put your summary stats into the options window just as you normally would. Make sure that pooled variances box is unchecked. And then for your hypothesis test, you're going to want to, generally speaking, you're going to keep that claimed value to be 0. So you're not going to do anything with it. Just make sure that the inequality drop-down menu there matches the same inequality you used with your alternative hypothesis, and then press compute. And out will pop your results window, and you read the test statistic right off the results window. It's always the second to last number there in the list. If we want to know what our p-value is, again, we're going to go to that same results window, and the last number there listed will be our p-value. Decide whether to reject the null hypothesis. So again, we're going to look to see, are we inside the critical region or outside the critical region? So here we have the t-calculator from StatCrunch, and I've put in the 1% significance level for our area, so our critical value now is negative 2.35. This is our critical value. And we can compare p-values with the significance level, or we can compare our test statistic with a critical value. Either way, we're going to need our results window. If we look at the p-value, we see that the p-value of 0.2499 is greater than, oh, that's a typo. It should be 1%. So therefore, we're going to fail to reject H0. What do we conclude from the hypothesis test? Well, here we have the same 4 options that we had previously. So the first question we ask is, did we reject H0 or fail to reject H0? Well, let's go back and look at it. We failed to reject H0. So therefore, we're going to want to select an option that says there is not sufficient evidence. That's answer options A and B. So right off the bat, we eliminated C and D. Now we want to know, should we say warrant rejection or should we say support? And we need to ask ourselves, do we have a one-tailed test or a two-tailed test? Well, we have a one-tailed test. It's because we have a match between our alternative hypothesis and our claim. So when we have that match, we're going to want to say support and not warrant rejection. Therefore, the correct answer option is answer option B. So remember, when we reject H0, we have sufficient evidence. When we fail to reject H0, we do not have sufficient evidence, or we have insufficient evidence. And we're going to say support the claim because our alternative hypothesis matches the claim. Confidence intervals in StatCrunch, you're going to use the same option that's used for hypothesis testing. The only difference is that now you're going to go down and click that radio button for confidence interval, and you want to remember to put the right confidence level there in the box. Also remember to leave that pooled variances box unchecked. Once you put in the right information into your options window, press compute, and now pops your result window from which you read your lower and upper limit. So, what is the appropriate confidence interval? Again, they're not telling you what level to make your confidence interval at. So, if they give you that information, obviously you want to just follow that instruction. But sometimes you're not going to be given that information. You're just asked what's the appropriate confidence interval, and so you have to determine what's appropriate. So when you get to your options window, you want to make sure that you take 1 minus 2 alpha for your confidence level. Why 1 minus 2 alpha? Well, as we learned in the last lecture, it's 2 alpha because we have 2 populations for our hypothesis test for our confidence interval, and not just 1. Therefore, the confidence level is 1 minus 2 alpha. So in this case, we would put 98% and not 99. In your results window, You then read the lower and upper limit straight off of the results window. So negative 2400.8 to 1307.8. This is our confidence interval. What do you conclude from these results? Well, to make a conclusion, you're going to have to look to see, is 0 inside or outside the confidence interval? Here, 0 is inside the confidence interval. Therefore, we have to conclude there's no difference between proportion of men and women who drop out. That looks like a typo. It's probably because it is a typo. So there's no difference between the average number of words that men and women speak. Remember that when you're talking about means, CIs are just as reliable as the more traditional methods of hypothesis testing. And here we see the same result. There's insufficient evidence to support the claim that men speak less than women. That brings us to the end of this lecture. If you have any questions, you know what to do. Otherwise, I will see you in class or the next video. Thanks for watching.